Let's go ahead and get started. There are two handouts at the beginning, at the front here. Everybody get those two handouts? Yeah. I hope you had a good fall break. How many of you came to the review session yesterday? Was it helpful? You went through those problems? Good. The problem list were the ones I didn't put on the midterm. There's one issue I would like to talk about right before class. It has to do with submissions. And I sent a survey last week about this. A few of you, actually, reasonable fraction, you submitted the same PDFs or very similar PDFs for your homework solutions. And I'm sort of baffled by that. I felt I made myself clear about the policy. I don't know exactly why that is happening. And I also don't know what to do about it. So if you suspect that you might be in a situation that you somehow accidentally or intentionally submitted the same PDF that someone else might have submitted in this class, I would like you to come either email me or come talk to me or help me resolve that. Because I don't think it's a good learning outcome for you to borrow text from someone. I really want you to, and I think I've said this several times, to write your own solutions to these. Because it really tests whether you've understood something or not. And the point of this class is not to just get a grade or get a good grade in this class. And that's really a waste of everybody's time because I'm happy that I can make this easy for all of us. And we can all just get A's and we can watch movies in class. But I don't think that would be a good outcome for any of us. It certainly would be much easier for me. And I don't think you'll learn that much. And I don't think that would be a good way that you're spending your money. So similarly, copying something from somebody else is not a good way to spend your money or your time. So I'd like to hear more about the circumstances of this. The survey was what I expected. Most overwhelming majority, the overwhelming fraction of you have understood that this is not the right way to learn in this class, and I've made it clear. So I'd like to know about that. The midterm is 4 questions. Feel free to give me feedback during the process. If you tell me how long you've worked on it and so forth, I'll use that feedback and perhaps, and I think this is quite doable in the time period, and I think the problems, as you know, now that you had 4 homework solutions that I've created, you know my style of basically taking the same techniques we discussed in class and applying them in slightly different ways. You'll find that the same in this problem set. So send me feedback as to how you're doing, how much progress you're making, when you finished 1, finished 2, and so forth. I'd happily accumulate those statistics and share them, and possibly use them to change our deadline. Right now it's Monday at 5 o'clock. The homework 4 solutions, they should have been available last night, but I emailed them to the TA to copy. There was a misunderstanding, and even today I can't get in touch with the TA. So I'll figure out some way for you to pick up a copy of that homework 4 solution for this midterm to help. The homeworks should have been graded. You should have had feedback. You should be able to receive the feedback online. If you're having trouble with that, again, let me know. And what else? I think with that, I'm ready to start the lecture. Any other questions or comments? In the back?
Are we allowed to reference our homework during the midterm?
What do you mean reference your homework?
Our homework submission papers, like the PDF that we submitted for the homework.
Well, that's a good question. Yes, you can look at your own submissions. Which is not to say that next time you'll put in your submission 50 pages of a scanned book so that later on you'll find it. Question?
Are we allowed to reference the textbook?
No. So the policy is just as I said with the following, you can look at what you've written. So I consider that question as, are my own solutions to the homework considered my own notes? And yes, they are considered your notes. The textbook is not something you wrote unless your name was Gorman, Fleishman, Revest, Stein, Weinberg, Pardosh. Anybody? Question in the back?
you shouldn't need any LaTeX advice. I will leave it to your own discretion if you're stuck with some compiled problem, but you've produced 4 homeworks, so yes, I'll leave it to your own judgment as to whether what you're looking at is really something about a LaTeX compiled problem. I don't foresee it. Anything else?
Do we still have to pay to that 2 pages per question?
Yes. Anything?
I'm sorry, I'm just still a little confused. So, we're not allowed to use the textbook. I understood before that we're allowed to use classes, or are we not allowed to use classes? It's like, are we allowed to use the slides that you presented?
Yeah, so the first part of the
midterm should say you're allowed to use your personal course notes and the course website and no other resources. Anything that's posted from the course,
like the lectures. Yep. Yes, those are part of your course notes. Really, I'm hoping that you can just look at this and say, aha, this is like this problem. I know how to solve this. I know how to solve this. I kind of know how to solve this one. This is kind of like that one. And then you'll sit on a nice rainy Saturday with a nice tea or coffee and finish it, again, in the solitude of your own thoughts. Today, we're going to continue our study of greedy algorithms. We're going to finish the Huffman coding
greedy algorithm that we started in class last Thursday. And then we're going to consider a new graph problem dealing with connectivity. It's a minimum spanning tree problem. And we're going to start studying the greedy solution for that graph problem. I want to make sure that everybody has this handout.
Many of you have implemented the Huffman algorithm, so you're familiar with it. We went over an example in class last Thursday. And what I want to do today is to show you how to prove that an algorithm like that is actually optimal, that it's the right solution. And you'll see that greedy algorithms, the first one we talked about and the second one we talked about, now this one, to show that they actually work is quite a bit of work. So it's counterintuitive in that it's often the first instinct that you have is to do some greedy local step. But they rarely work. And when they do, it takes a bit of effort to show that they work. So that's one lesson you should get from these things. Nonetheless, when they do work, they lead to these very elegant solutions like the Huffman code, where with the priority queue, you can very quickly find the optimal prefix-free coding for a given frequency.
Do you have the... Fantastic. All right, everybody, let's give us a round of applause. Okay, I'll show you how in the copier there's a button that says staple. When you push that button, the copier does the work for you. But thank you. And after class, we'll distribute these, okay?
I think we could have convinced him to get a stapler and actually staple them, huh? Huffman coding. Remember our guy here, Samuel Morse, the artist who invented Twitter in 1845 and also came up with a very short coding scheme for short messages. He had the following problem. You're Alice and you're Bob, and you want to send this particular message. You need to find some way of encoding the characters in your alphabet in the characters of your communication medium. This communication medium consisted of short dashes and dots, or ones and zeros and twos, twos being the long spaces between words. Why did you need the twos? We'll talk about that in a second. But the goal of this exercise of encoding is to find a very efficient way of sending a message. And the way we represent that is by this function BT, which is the cost of a particular encoding for so you suspect the messages you're going to send are going to obey some set of frequencies, some distribution. And now you'd like to compute the cost of sending messages in that message space is going to be essentially the sum of the frequency of character C times the length of character C in your encoding. That's going to be the cost. And you'd like to find a minimum cost for the given frequencies that you have. This is a default sort of ASCII-like encoding. And as we saw on last Thursday, this is suboptimal. And why is it suboptimal? Because all characters don't have the same frequency. So any Scrabble player knows that certain characters are more likely than others. And so perhaps the idea is to make more frequent characters have shorter codes. That would lead to more efficient encodings. Morse came up with such a scheme, but the problem is that it was ambiguous. Yeah, you could have a certain message like this that decodes in several ways. And the way they solved it is by adding a third character in their alphabet. So they had dot, dash, and space. And so you can separate words. That makes it a little bit less efficient. Now you have to, the time it takes to send a message is slightly longer because you had that extra space between words. And as we found out, it's actually completely unnecessary because there is a notion called a prefix-free code. And the property that a prefix-free code has is for any two characters in the alphabet, if they're not equal, then their codes are not a prefix of one another. One code is not a prefix of the other. When you have such a coding, here is such a prefix-free code. It is easy to see that you'll never have ambiguous messages because the prefix of every message will be uniquely terminated by some code. And then you know that that's the only character that prefix could represent. You can output it, delete it from the beginning of your message, and iteratively decode the rest of your message. A nice thing about prefix-free codes, is they have a one-to-one correspondence to binary trees. We talked about this last time. So if you're given a code, you can turn it into a binary tree just by following, taking each character and turning it as a left or right branch in your tree. And so once you have a tree, then it's very easy to encode messages, or it's very easy to decode messages. You just take each character of your message and follow this tree until you hit a leaf. Once you hit a leaf, you output that message, and you continue in your stream. So having this one-to-one correspondence makes encoding very, very simple. And similarly, if you have a binary tree, you can turn that into a prefix-free code just by doing a traversal of that tree. So this is an example of a binary tree for this alphabet. This is an example of the codes that you get and the lengths of those codes, which are now not necessarily the same for every character. Great. So what is the goal of this project, this Huffman coding project? Well, we are given as input, we're given character frequencies like this for every character in our alphabet right here. And what we'd like to do is produce the prefix-free code T that has the smallest costs for those frequencies. Right? Everybody familiar with that? Understand what the task is here? Okay. And last class, we saw, okay, well, before I get to this, last class we saw an example of how the algorithm works. It iteratively, the solution, the Huffman solution is to take the two lightest characters, the least frequent characters, and combine them, making a new node, and then solving the problem that has n-1 characters in it. It's a greedy solution, and it's very elegant and very efficient and easy to implement. Now, today's lecture, we're going to discuss why that's actually the optimal solution. And the first step into determining why it's optimal is to understand the following lemma, which is that an optimal tree must be full, which means that each leaf, each node, the optimal tree must be full, meaning each node in this tree must have either 0 children, like these nodes right here, or 2 children, like these nodes right here. Now, why is this the case? So if some node only has 1 child, like that right there, then what can you do? Then it can be removed So if there was a tree that had that node with a single child, then you can actually transform it to this right here. Let's suppose this was X. You can just remove that middle child right there and have a tree that was shorter. And in particular, in this case, you can also remove that and just produce that root tree. So every node must have either 0 children or 2 children. So one idea that you might consider, right, is to partition a natural idea you might have is to say, take your frequencies, partition them into 2 halves that are roughly the same. You can do that, for example, using the tug-of-war algorithm that you solved in homework 4, and then just make a tree that's like this, where 1 half of it's on the left and 1 half of it's on the right. This is a natural algorithm you might come up with. But there's no reason here to believe that an algorithm like this is actually going to be optimal. Here's an example right here, 5 characters, and you can partition these . Okay, so imagine a code where so if we were to run that construction on this right here, notice that the weight of this right here is 50, and the weight of this set right here is also 50. That would produce a code something like this. Yeah? Question? Shouldn't what? Yeah, sorry, it'll be like this. Good. Yeah, so the problem here, notice that O has a the length of O is equal to 3. Even though O is a fairly common character here, it has a very long code word. So this scheme is not optimal. So partitioning it, trying to divide and conquer like this, it just doesn't fit with the function that you're trying to minimize. And I think I have a better code here would of course be the Huffman code, which would put U in P. Right? You can see that this is not going to be optimal, even without knowing what the optimal solution is going to be. Notice that U has a code, length of U is 2, okay? But U, so in other words, length of U is smaller than length of O, but frequency of U is also smaller than frequency of O. So this is not good. O has a 3-character alphabet, and if you just switch O and U, if you just were to switch O and U, you'd get a solution that's smaller. Okay? And so keep that in mind, that switching two things could possibly get you a smaller code. We're going to look at that again in just a bit. Okay, so this was an example run we did last time of how the algorithm actually works. I'm not going to do it again, or I thought I'm not going to do it again. Yeah. So let's get to the heart of it, right? So what we'd like to show and this is going to follow in 2 lemmas. Two-step proof. The first proof. If x and y are the least frequent characters in our input, then there exists an optimal solution in which x and y are siblings. Now we're going to show this as follows. Now you can work along with this on the handout. Consider an optimal solution T in which x and y are not siblings. So we can draw a picture of that. It's going to look something like this, like you have on the handout. You have some tree T, and here x and y are the least frequent, but they are not siblings. What we're going to do is we're going to swap. We're going to find some pair A and B, and we're going to swap x with A and y with B, and we're going to arrive at a solution that's no costlier and has the property that we want. So how are we going to do that? So, first, since T is optimal, what property can we say about T that we've discussed so far? Yep. Great. Since T is optimal, T is a full tree. Let A and B be the leaves with the Since T is optimal, T is a full tree, and so we let A and B be the leaves that have the greatest depth. And since T is full, that means every node has either 0 or 2 children. So A and B, there has to be some pair A and B which are siblings that are at the greatest depth in this tree. And in fact, these are those 2 nodes right here. And so, without loss of generality, let's say that the frequency of A, in fact, the frequency of, let's say a few things. So, since X and Y are the characters with the least frequency, then we can say that f of x is less than or equal to f of a, and f of y is less than or equal to f of b. And we're going to do 2 exchange operations. In the first step, we're going to transform this tree into T prime here. Our first step, we're going to basically do this swap right here. This is number 1, and this is number 2. Okay. So this first step, let's see if this is. Okay, this is the slide. Remember these 2. Remember, this is the only part we need right now. So this is what I want to say. Let's consider B of t. So the part that I've circled in black, I'm going to call C. And do you agree that the costs for both of these trees are as stated? So the cost for this tree T is going to be the cost for this part that's C, that's the same in both of these trees, plus the frequency of X times the length of the code X, plus the frequency of A times the length of A. And similarly here, the only difference is it's the frequency of X times the length of A, because we swapped the two, plus the frequency of A times the length of X. Does that make sense? Okay. So now what happens when we consider the following? Suppose we subtracted the two. What do we get? Well, the factors C are going to cancel each other. And what we're going to have is f of x times L of x plus f of A times L of A minus f of x times L of A minus f of A times L of x. Now we can combine these terms as follows. Now, I'm going to rewrite this as let me do it right here. So what did I do? I skipped a slide because I skipped a step because I'm running out of space. But what I did is I factored -1 out of this. I made this negative, and made this positive. Does that make sense? So then, all of a sudden, this term right here inside is FA minus FX, which is the same as this one. And then this is LA minus LX. The reason I did this step, what do we know about this term right here? Great. And what do we know about this term? It's also positive. And so as a result, if the product of two positive numbers is going to be positive, or greater than or equal to 0, question. Why were we able to make these assumptions? Well, notice that these two are arbitrary just by naming. Okay? And now, since we know that f of x is the smaller one, then we might as well just, and it's the least one, we might as well just pair them this way. So in other words, it's just a way of naming them. I've just named, there's x and y, pick the smaller one, call that x. There's a and b, pick the smaller one, call it a. And now the smaller one has to be smaller than the smaller one, and etc. Now, what's the point of this? We've showed that the cost of tree t minus the cost of t prime is greater than or equal to 0, but why do we care about that? Yeah? That's right. So this is the cost of the optimal one. This is our tree. And so this really has to be 0, and that means that b of t prime is also optimal. Okay. So now you know the game. What are we going to do next? Exactly. Now we're just going to do the same thing right over here through the same argument. And now we have the following, right? We have so what this shows is that in an optimal tree, we know that the two smallest characters, the two characters with the smallest frequencies, they are going to be the lowest, and they're going to be siblings. So that kind of justifies the first step of our Huffman. Remember, we take the first two characters and make them, we combine those two. And so we at least know that they're siblings in the final solution, which we force them to be because we pick those two and combine them. And intuitively, they're also going to be the simplest at the lowest depth, which we still have to show. Did everybody get this simple lemma? Great. So I hope we have, I'm going to keep that exchange argument there. We're going to need it. Okay. The next lemma, the next property we have to do is this optimal substructure problem. All of our greedy problems have this optimal substructure problem that solving a problem of size n can be reduced to solving a version of the problem of size n minus 1 or smaller. Like the scheduling problem had that same situation. We take the first one and then find the best schedule of the remaining one. That means we can reduce the big problem into a smaller one, find the best solution, and combine them. Just like divide and conquer, just like the dynamic programming, we just had a more clever and local way of making that transformation. So here we're going to have to show, this is going to be the final part of the proof for Huffman, that Huffman has this optimal substructure too. And what does that mean? That means, suppose we're given inputs FC as follows. Okay? Now, what we want to argue, what we're doing is taking the smallest two, combining them, taking the smallest two fx, fy, producing an fz that's the sum of those two, and producing an instance fc prime that's of size n minus 1. That's what we're basically doing in the Huffman algorithm, right? This is the algorithm. Take the two smallest, combine it, get a smaller problem, and find the best solution of that one. So the question is, why does this work? And here is when we're going to actually get to the heart of it. It's a subtle argument. So the lemma we're going to state is that so the optimal solution for this problem is to compute the optimal solution for fc prime, this is prime right here, and then replace whatever node we have for z, we're going to replace it with this structure right here. That is, once we prove this lemma, then we know that Huffman actually works. Okay, yeah, so this is the solution for fc prime. This is going to be the solution for that's what the lemma shows. Okay? And now to prove this, so how can I express the cost of t prime in terms of the cost of bt? What do I have to do to bt in order to correct so that that equation is? What do I have to do? Where are the two trees different? Right. This is going to be f of x plus f of y times Lz. And this, the cost of this tree is going to be f of x plus f of y times Lz plus 1, right? Because the tree is, the path, the code for x and the code for y is basically one character longer. So what do I have to put right there? What do I put right here to make this equation true? Yeah? Exactly. The codes for x and y are just one bit longer, and so the cost for this tree is just going to be plus f of x plus fy. Everybody see that? Here is the punchline. Suppose our tree T suppose our tree T over here on the right is not optimal. I.e., there is some other tree Why is that going to be a problem? Well, let's see. So we have some tree, U, that's going to be smaller than BT. And now, consider the tree where we take these two nodes and compress them. So imagine that we take this tree right here and just compress it and make it that Z node. What is BU? Based on this slide, what is BU? And what do we know about BU and BT? We know that BT is greater than BU. So if this is equal, this would be true. And now what do we know about this quantity right here, BT minus FX minus FY? That's equal to this would mean that, what would this mean if BT is greater than, BT prime is greater than BU prime? What is the one thing we know about BT T prime? How did we start this proof? The first thing that should have been written on your paper as you're following along, this would mean that T prime is not optimal So what we've just shown, we started out assuming that we had an optimal solution for the smaller problem. And if we did the substitution, suppose we get something that's not optimal. Like this. Well, then that means that there's something smaller for the big solution, which means that there would have to be something smaller for the smaller solution. This is essentially what it means to have optimal substructure. Does that argument make sense? Isn't it such a beautiful, clever argument? My story was wrong. Huffman wasn't an undergrad, he was a grad student. And he had the choice of either solving this open-ended problem that his advisor had not been able to solve with Claude Shannon, the founder of information theory, for several years, or he could take a final exam. So those were the two options, and he really didn't want to study for that exam, so he knocked this out. Yes, I'll make a list of problems which you're welcome to solve, and if you do, no final exam for you. All right, so what do I want to say? That's basically the lemma. You see, one question. Here, I have a challenge for you. We are making an assumption in this proof. So the question I have is that I wouldn't just make you prove something that was completely irrelevant. And the first thing we did was we proved this lemma. Lemma 1, that the two characters with the smallest frequencies are both the same. Where do we use that in this proof? Spend 2 minutes with the neighbor trying to figure out why we had to prove lemma 1. So clearly lemma 0, I think about the optimal treatment tool, that was needed in lemma 1. But so far in lemma 2, where are we making use of any other fact? All we're saying was, suppose we start with t prime, which is an optimal solution. Suppose t is not optimal, then we make that first indication, then the second thing, and then the third thing. Where are we using lemma 1? Spend 2 minutes with your neighbor, try to figure that out. More time? Okay. So where did we use lemma 1? And it's a trick because what did I do? The structure of this proof started by saying let t be optimal. This is something true about t prime. Okay? And now suppose that t, right, t is defined by taking t prime and changing that node z with x and y. And now we said, well, suppose this t is not optimal, then there had to be some other u that was optimal, that had a smaller score. Then on the next slide, I just said, well, this is how u has to look. I just drew it like that. Why does it have to be like this? Exactly. So in particular, by lemma 1, we know that x and y must be siblings in U. So we use lemma 1 because this is how we're saying that the structure of U has to be like this. X and Y have to be siblings at the lowest level. And that means that we could then combine X and Y into Z. And now all of a sudden this is a candidate solution for FC prime. 1 second. If X and Y here, if they weren't siblings, if X was over here and Y was over here, then there would be no way for us to combine them into a solution that that involves Z, i.e. a solution that could be possibly a solution for FC prime. Question? Sure, and that's true. In fact, all I need in this group right here is a C. All I'm going to do is take X and Y. Since they're siblings, all I need in this proof, the fact is that they're at the lowest depth, all I need is for them to be siblings so that I can take this triangle and make it into this Z. If they're siblings, I can squash them. And if they're siblings, then this relationship holds. We are using lemma 1 to get this structure, and then we're also using lemma 1 as a consequence, this equation holds. Because this equation holds, we can then conclude this and this. So it is an integral portion of this proof. And that's why we had lemma 0, so that we can prove lemma 1, so that we can prove lemma 2. Get the sense that it is a subtle property here, which is why Fano and Shannon couldn't find the solution right away. Good? Question?
So in other words, you could say, let U be an optimal solution. On level 1, let U have an optimal solution. On level 1, there's U also optimal. Take whatever optimal, transform it into something like this. This right here, this follows because of this right here. I think drawing right here, this drawing right here. So the cost of this tree is going to be related to the cost of this tree by the fact that x and y are just going to have the length of the code for x and the length of the code for y is just going to be LZ plus 1, where LZ here was the length of the code for LZ. But what I'm saying is first B of U prime is equal to this. Then I'm saying that this sum upper bounds that sum. Then I'm saying this is equal to that one. So if you put all of these together, then BU is, this implies essentially that the U prime is smaller than the T prime. Is that the question? Onward. The next problem we're going to consider, a very interesting and very well studied problem. It's called the minimum spanning tree, and here's one motivation for it. So you have the first person that moved to Charlottesville. At some point, they built their cabin out in the middle of the woods. Excellent. And pretty soon people realized that there was a nice place to live in this area, so someone else built a little house. And now there are two people within a few miles of each other, and they wanted to see each other occasionally, so they would, of course, build a little trail or path with a machete forge through the vegetation and the brush that was here like several hundred years ago. And they at least made some way for them to see each other once in a while, because I think a very intrinsic desire for humanity is to be social and interact with other people. Soon, other houses came up, and eventually Charlotte became a ville, Charlottesville. So there are many other houses, and the problem emerged since all of these houses came up all at the same time. They heard through the Twitter network that this was a great place, and so they came here quickly, built their house, and now they had the same problem, which is they wanted to see each other. So they wanted some way to get to their neighbors' houses. Right? You can imagine a city, if you've played the game SimCity or all of those type of things, you have to put roads so that people can see other people, right? In fact, that is the motivation of this particular problem. So you can imagine that all of the houses are connected by, these are possible edges. We can build a road, we can build this road, or we can build that road or that road. We don't have to connect every pair of houses to one another. We just have to make sure that if you're at some house, you can always get to whoever your friend is, wherever they live, you can eventually get to their house, right? So you might consider the possible edges in this network, and then consider a graph like this. And now the problem is you want to create a network so that anybody can get to anybody else's house eventually, but you're also resource efficient. You want to spend the least amount of money making roads.
So this is a generic network connectivity problem. It's known as the minimum spanning tree. So let us try to formalize this problem. First, we have to formalize this notion of graphs. I know all of you have taken the earlier courses in our sequence, and you discussed what a graph is. Here's another resource in chapter 22 of CLRS. Very briefly, a graph is going to consist of a set of vertices and a set of edges. And in our special case, we are also going to have W. Okay. This is going to be the weight it's going to assign, this is a function that assigns each of these edges right here in the graph some positive weight. Later on, we'll talk about situations in which edges can have negative weight, and we'll see what that implies. Good. So there are a few ways to represent graphs, and the way you represent them actually affects how efficient your algorithm can be. The first way is an adjacency list. So the way this works is you have, this is an array for each of your vertices. And you know how this works. A basically has a linked list to all of its neighbors. So A is connected to B, to C, and to D. B is connected to A and D. So, such a data structure allows you to do all of these computations on graphs. But let's analyze this. How much space does such a data structure take? Well, in terms of the size of V and E, it actually takes, right, this array is going to be of size V, and then the number of nodes in this list is going to be exactly proportional to E. Right, or maybe 2E, because the edge from A to B is going to be represented twice. Okay, so it's going to be order B plus E. In order to figure out the neighbors of a particular node, how much time is that going to take? It's going to be order number of neighbors. If A has 3 neighbors, it takes 3 steps to list them all. You just walk through this list. What about the time to check an edge? If I want to see whether D has an edge to B, how much time will that take? Yeah. Which could basically be order the size of V. In the worst case, it could be order the size of V. This is one way to do it. You know the other way. And here, you keep a matrix, and you put a 1 at every spot like this. How much space does this representation take? V squared. How much time does it take to list all the neighbors? V, because you basically have to scan through this row looking for all the ones. But how much time does it take to check an edge? That's right. You just index a spot and see whether that edge is 1 or not. Okay, so there are trade-offs in the time complexity of this type of thing. A few basic definitions. I'll go over these in the next class. So essentially a path is what you think it is. A connected graph is essentially a graph in which for every pair of nodes there's a path which connects those pairs of nodes. And a tree is a connected graph with no cycles. What we basically want is a way to connect each pair that has minimum cost. And this is precisely the notion of a minimum spanning tree. We are going to consider 2, possibly 3 solutions to this problem. The first one is a very simple one. Let me just explain what the algorithm is. We know that the solution, we're going to argue the solution has v minus 1 edges in it, and we're also going to argue that the solution has no cycles in it. Why would the minimum spanning tree not have a cycle? Yes. If you had a cycle in your solution, then you could just remove that one edge from that cycle and get a cheaper solution and still have the same connectivity. So the minimum spanning tree is not going to have a cycle, and by a pigeon argument, we're going to show that it has to have at least v minus 1 edges in it. So a natural greedy solution is keep taking the lightest edge that doesn't create a cycle and do that for v minus 1 times. And this is how that kind of solution looks. So here's an example graph. The lightest edge is this one, so we take that one. Doesn't create a cycle. This edge doesn't create a cycle. This edge doesn't create a cycle. Now what about the next 3? That does create a cycle, so we have to skip it. What's the next edge we take? 5. Next one. 6. Next one. Next one. Now what about this 9? Cycle. What about this 9? 10. And then we're done. That's a minimum spanning tree algorithm. This is called Kruskall's algorithm. We'll study this one, and we'll study Prim's, and we'll study, there have been 50 solutions to this problem, and we still don't know the best one.